All right, this is the 2019 AMC 10B problem number 11. Two jars each contain the same number of marbles, and every marble is either blue or green. In jar 1, the ratio of blue to green is 9:1. In general, when you see a ratio written with a ratio symbol especially, just add a little x next to both as a scale factor. This is jar 1. The ratio of blue to green in jar 2 is 8:1. So you'll make it 8y to y. You can't use x because the scale factor is not the same. There are 95 green marbles in all. So let's pause here. Before we read the rest of the question, let's make some progress instead. It says the same number of marbles are in each jar. So you can add 9x plus x, which is the blue to green ratio, and you will get 10x. That has to equal 8y plus y, which is the total marbles in jar 2. Therefore, x is 9/10 of y. All right, this is a new piece of information. Again, in general on the test, you're trying to generate new pieces of information, which you will then capitalize on to find an answer. So next up, there are 95 green marbles in all. Well, green was x and green was y. And so we know that x plus y must equal 95. I'm just going to substitute in to get 19/10 y equals 95, multiplied by the reciprocal times 10 over 19, and this will go in here 5 times, and y will equal 50. And since x is 9/10 of y, x is 45. Now come back. How many more blue marbles are in jar 1 than jar 2? You might want to, by the way, check, is 10 times 45 the same as 9 times 50? It is. This is how you avoid silly mistakes. Checks like that take 2 seconds, 3 seconds, and you can be more sure of your answer. Okay, so we're just going to do 9x minus 8y, because that's the blue here and the blue there. 9 times 45 is 9 times 40, which is 360, and 9 times 5, which is 45, giving you 405. 8 times 50 is obviously 400, and the answer is A, 5. All right, this is the 2019 AMC 10B problem number 12 done by request. Later I'll probably add it to a video of 11 through 15, but for now, because we're so close to the testing time, I'm just trying to get out as many requested videos as possible. What is the greatest possible sum of the digits in the base 7 representation of a positive integer less than 2019? The first thing that we're going to need to do, we need to know what 2019, and this is in base 10. You can tell because there's no subscript 7. We need to know how big that is in base 7. So we're simply going to convert it. Now, how do we do that? We know that in different bases, it'll be something like times 7 to the 4th plus blank times 7 to the 3rd plus blank times 7 squared plus blank times 7 to the 1st plus blank times 7 to the 0. Now, we want to know if 7 to the 4th goes in. 7 to the 4th is 49 squared, and 49 squared is 50 squared minus 99. This is 2,500 minus 99 is 2,401. If you want to know why this is true, I'll explain it at a different time. So 2,401, though, is 7 to the 4th. That's too big for 2019. So we know there is no 7 to the 4th term, and consequently, I don't actually need it. So we start with 7 to the 3rd. 7 to the 3rd is going to be 49 times 7, which is 343. You want to know how many 343s can we fit inside of 2019. So you'll do 343. Obviously, there's not going to be 7, because that would put you at 2,401. However, we can probably get, let's try 5. So 5 times 3 is 15, 20, 21 to 15, 17. If I add 300 to this and 43, it's going to go over 2019. So we're pretty confident then that this is 5. Not just confident, we know. What you do next, this number has to be subtracted from that to see what's left. So you do 2019 minus 1715 to get 304. Next we take 304 and we go to 49 and we ask how many 49s can fit. It's about 6 times 50, so it's definitely 6 times 49 will be smaller than that. What is 6 times 49? It's 294. You'll subtract again to get 10. All right, then you take this 10 and you say how many 7s can fit into the 10. That's going to be 1 7, and you'll put 7 and subtract, and there's still 3 left, and that is your units digit for base 7. So we can say that this is equal to 5613 base 7. This problem is basically a knowledge check on number 12. You either know the concept of how to convert to a different base or you don't. And if you know it, you're going to probably get it right. And if you don't know it, you're probably not going to get it right. So it's good to understand this stuff. So this number here, we want to know the greatest possible sum of digits in base 7 representation. Again, something to remember about different bases is you can never have a number in the digits that's equal to the base or higher. So we can have no 7s amongst our representation here. Obviously, 6 is the highest number. We would like to have as many of those as we can. Can we make 5666 base 7? We can't, because that's bigger than 5613, and hence it'll be bigger than 2019. So this is out of the question. But if I take the 5 and reduce it by 1, 4666 base 7, that's okay. We can sum this to get 18 plus 4 is a sum of 22, which would be this. But we want to check to make sure we're not making a mistake, because 23 is really close to that. Maybe we can get a little bigger. And you want to avoid, trap answers and such. So is there a way we could have, instead of 6 right here, we had a 5? We could bring this 6 down to a 5 and have 5566. But clearly we've exchanged the 4 for a 5, which is plus 1, and the 6 for a 5, which is minus 1. Or we can simply add and realize it's also equal to 22, which will be our answer. All right, this is the 2019 AMC 10B, problem 13, which was also the AMC 12B, problem 7. What is the sum of all real numbers x? It's a good idea when you're taking the test to underline keywords like real, because it informs you that the values you get could be irrational, they could be fractions, they could be negative, things like that that you need to be thinking about as you progress in the problem. All real numbers x for which the median of the numbers 4, 6, 8, 17, and x is equal to the mean of those 5 numbers. So we should consider how is this going to work, and let's make some cases. The first case will be if x is to the left of 6, right? What will that make the mean? We don't know where x lies. It could be below 4 as well, or the median, but we can see that 6 is definitely the median in that scenario, even if I switch x with 4. So if x is less than 6, the median will come out to be 6. The next option is that x is between 6 and 8. Now, if x is between 6 and 8, then x is the median. And lastly, if x is greater than 8, then it will make 8 the median. Okay? Now keep these in mind, because there's several trap answers in this problem that are kind of convincing if you didn't think about it carefully. Let's start with x less than 6. It says that the median, which will be 6, is going to be equal to the mean of these numbers. Well, let's add up what we got. 4 and 6 is 10. That's 25. 35 plus x is the sum, and we have 5 numbers. Immediately multiply by 5 to get 30, and you will see x is negative 5. Now, is this okay? Yes, x is less than 6, and it's real, so it's okay. Negatives were okay. All right, we go to the next one, x between 6 and 8. Now we'll have this exact same setup, 35 plus x equals, x is the median. We know it's divided by 5. Don't even write it. Just multiply by it right away to save time. Subtract x to get 4x equals 35, and x equals 35 over 4. Now we know 36 over 4 is 9, so 35 over 4 is 8.75. Now, check now, is 8.75 between 6 and 8? It's not. Therefore, the answer is invalid. If you decided to use it, I believe you would get one of the false answers, but I'm not certain. Let's go to the next one. 4 plus 6, again, we know the whole thing. It's 35 plus x divided by 5. This time needs to equal 8, so when you multiply by 5, you get 40, and x equals 5. Now, if you're not thinking and you're in a hurry to get to the next question, you're going to go 5 and negative 5 is 0. I got it. I'm so good. And then you're going to get it wrong. Don't do that. Make sure you're checking. Is 5 greater than 8? Well, no, it's not. So that doesn't actually work. And the only possible solution is negative 5. Continuing on with the 2019 AMC 10B, problem number 14. The base 10 representation, and again, base 10 in other words means normal, because we don't have to worry about anything weird about it. Representation for 19 factorial is, and it's a bunch of garbage, don't read it, because you're not going to know what you read anyway. You have to think about billions and trillions and crap like that. Some big number. Where T, M, and H denote digits that are not given. What is T plus M plus H? Okay, so we have to think about a plan of attack. How are we going to attack a problem like this? Again, we know it's equivalent to 19 factorial, so let's target what we know. We're probably going to have to use numbers that are part of 19 factorial that have good divisibility rules that are fairly restrictive. Something like 11 has a pretty good divisibility rule, and it's really hard to make something divisible by 11, so we'll use that for sure. And 9 has a pretty good one, which says the sum of the digits must be a multiple of 9. Now, aside from that, since we're going to use divisibility rules, there's another aspect of factorial that might make our lives a little easier. When you get 5 factorial, that's 120, but 4 factorial is only 24. What happens between here and here is you gained access to a 5, and because there were powers of 2 in here, you gained a 0. Well, then that stands to reason that every time you go up to another 5 in your calculation, you're going to gain another 0. And so at 15 factorial, we're going to end in 3 zeros. Now, 15 factorial is part of 19 factorial, and therefore, h must be 0. Okay, so now we just need to find what t plus m is, and we continue with our reasoning. The rule for divisibility by 11 is that you add up every other digit going through, and then you subtract all the digits you didn't add the first time, and that result needs to be a multiple of 11. It can even be negative multiples like negative 11. So let's start with that. 1 plus 1 is 2 plus t plus 1 plus 0 plus 0 plus 8. So we've got plus 1 plus 8 plus 2 plus 0. All right, then this is 10, 11, 12, 13 plus t minus now what's left, which is the 2 plus 6 is 8, plus 5 is 13, plus 0 plus 4 is 17, plus m, plus 3 plus h, which is also 0. So I get 13 plus t minus m plus 20. That is t minus m minus 7. Okay, this needs to equal something like negative 11 or 0 or 11. It could be 22, but it's highly unlikely. Actually, it probably couldn't be. But just try these out for sure. Then what? We also need to check for divisibility by 9. So we're going to add up all the digits. We know that these already sum to 13 plus t, and we know that these sum to 20 plus m. So we get 33 plus t plus m needs to equal a multiple of 9. Now, our only options are going to be 36 or 45. Why can't 54 work? Because it would require t plus m to equal 21, and that would require a digit of like 10, and we don't have access to that in base 10. So no 54. If it's going to equal 36, you'll get that t plus m equals 3, or t plus m, if it's equal to 45, will equal 12. All right, we'll notice then that this is what t plus m plus h is one of these two things, which is only A or C. In the event that you got stuck here, it is only 14. You probably shouldn't be getting stuck here, but you could conceivably guess if you get down to those two answers. I don't recommend guessing in general, though. Okay, so continuing on then. Let's say it was negative 11. Then t minus m would equal negative 4 when I add 7. Or we can get t minus m equals positive 7 if I have 0. Again, you're adding 7. And lastly, t minus m could equal 18. We're just going to try different combinations of these out. Let's start with the 18 because I already know what works. So t minus m equals 18. What's going to happen when you add these is you're always going to get 2t because they all have a negative m. We can take advantage of that to save our calculation time. Obviously 30 is too big because t can't be 15. Again, over here I'm going to get 2t equals, if I have 18, I'm going to get 21. That's a problem too because it's not a digit. So we know that this is out. Let's go to t minus m equals 7. So if I put a 7 here, it'll say 2t equals 19. Not going to work. Put a 7 here, I'm going to get 2t equals 10, which would give t equals 5. Hey, that could work. Actually, it can't because m is negative 3 in that case, and you can't have negative digits, so that doesn't work out. Then we go to the last case, which is t minus m equals negative 4. If I do it here, I'm going to get 2t equals negative 1, 3 plus negative 4. That's not possible. Here, if I picture negative 4, 12 minus 4 is 8. I'll get 2t equals 8, which means t can equal 4. Now, this doesn't say this. It says negative 4. 4 minus m equals negative 4. Well, then m must be 8. Now, let's check it here. 4 plus 8 does indeed equal 12, and this is the only case that works, so we know it is C. All right, continuing on, the last problem of the set, 2019 AMC 10B problem number 15. Right triangles T1 and T2 have areas 1 and 2 respectively. If you get hung up on this word, it just means that in the same order that T1 and T2 appeared, 1 and 2 match. So 1 goes with T1 and 2 with T2. A side of T1 is congruent to a side of T2, and a different side of T1 is congruent to a different side of T2. Notice they don't say legs, so don't get hung up on that. What is the square of the product of the other, which is the third sides of T1 and T2? It's kind of almost overwhelming a little bit to think about this. Let's forget the last sentence then and not worry about the third sides, and let's set up a picture that helps us think about what's happening and work from there. We'll start by making a triangle 1. Just make any random right triangle. Call it A, B, and C, for instance, because we know Pythagorean theorem uses the same letters. Then consider T2. Is it possible that the shorter leg of A matches the longer leg of T2? Don't forget, T2 has the same area as its subscript as does T1. So if A was the longer leg of T2, that would force the shorter leg to be shorter than A, which would make T2's area too small. So A is not going to go here. What if A went here? If A went here, in order for T2 to have twice the area, it would have to be twice the other leg. Now, that would cause you to get the square root of A squared plus 4B squared here, and this is the square root of A squared plus B squared. So clearly their hypotenuses cannot be equal, and furthermore, this cannot equal B because the square root of 4b squared is at least 2b, so this doesn't work as a setup. So we can't have this. It tells us for sure that A is not going to be equal to any of these sides. So that means that B and C have to be the two equal sides to the other triangle. It's not going to make sense if B becomes the hypotenuse of the other side. B can't be the longer leg. That would make this one probably get too big. Let's make B go here as the shorter leg. then if C was the hypotenuse, it would force this to be A, right? If B went here and C went here, it would force this to be A, and you'd have the same triangle, so that wouldn't work. So B has to go to the shorter leg. C, the hypotenuse of T1, must be the longer leg of T2, and we'll call this D. Great, now we are set up. Now we can make some further calculations or pieces of information that we can generate. Since the areas are 1 and 2, it must mean that half AB is 1, which means AB equals 2. And furthermore, BC will equal 4 because half BC is 2. We multiply to get 4. We also know that A squared plus B squared equals C squared here, and B squared plus C squared equals D squared. Now before progressing further, let's think a little bit now about the end. What is the square of the product of the other third sides, the non-equal sides, in other words, of T1 and T2? Those would be side A and side D. So we can think of it as A times D squared or A squared times D squared, whichever proves more advantageous later on. So we'll think about that in a second. We can see that we have an A squared here. We also see that we have AB equals 2 and BC equals 4. This means that I can write A in terms of B and C in terms of B. And if I do that, I can now solve this for B squared or B or whatever I want with that regard. So let's plug these in. We're going to get 4 over B squared plus B squared equals 16 over B squared. Multiply by B squared, you're going to get B to the 4th here. These are going to disappear, move the 4 over to get 12. So once we've done that, we don't really want B to the 4th, but do we really want the 4th root of 12 for B? Probably not. Let's just go down to B squared and call it root 12. Don't even bother simplifying or rationalizing. It doesn't really matter. Now we can come over here and figure out what A is. We know that A squared equals 4 over B squared. So then we can say that A squared is equal to 4 over root 12, and that's one of the two things we need. So we have 4 over root 12 times. Now we're going to come over here to B squared plus C squared equals D squared. We already know that C is 4 over B, so C squared is 16 over B squared, and we have B squared plus that is equal to D squared, but good luck, we know what B squared is, a good thing for us. We can just plug root 12 in. So you're going to get root 12, which is B squared. Don't accidentally square it. It's B squared that's root 12, not B. So root 12 plus 16 over root 12 equals D squared. To make this one nice fraction, let's multiply this one by root 12 over root 12. That's going to give us 12 over root 12, which adds to 28 over root 12. We simply put that over here. We are so close. We just got to round third base and head for home. All right, this is root 12, so the root 12 times root 12 becomes 12. 4 goes into 12 3 times. We're done simplifying. Our answer is A, 28 over 3.